Okay. Hi all together. As I told you last time, today the idea is to show you the simulation of SIR system. But before showing the simulation, I would like to repeat very quickly what we did. And I would like to apply the first theorem at the system. And since we will try to classify, to analyze the equilibrium points or let me say the equilibrium sets, which we have in this kind of system. Let me now switch on the lateral camera. What I need is. Yeah. Exactly. Sets or the manifolds, we will see a little bit the difference also, even though I don't want to go really in depth on this, because the nomenclature for us is not really important, but just to understand a little bit the difference between points, sets, manifolds are basically sets. What happens here? Let us switch. Yeah. You remember, this was the system including also the equation number 3, yeah, in which, do you remember, we assumed that yeah, the system is somehow closed. No? Means we don't have new children, let me say, in this sense, and not only the recovered people. The recovered people is just the integral of the infected, which basically don't consider people who died without being infected in a sense. You're right that here we have to consider plus UV. No, we discussed also last time. If I here include a minus UV, I mean, the vaccination reduce the number of susceptible people. This means given a direct contribution, negative contribution to the derivative. This means we reduce this. Yeah, I forgot to put it because, again, this is a variation. If you look in the literature, for instance, Wikipedia, and SIR is without this one, basically it's an autonomous system without any kind of inputs. Possible inputs are vaccination here, as in this case, and eventually also here in the quarantine. Could be an interesting project for you, directly here. But the model, the general model, which is here, could be used in any competition system, which we see in a possible competition between populations, between populations. The concept of the population is also a general concept. No? We can consider, again, animals, folks. Folks is what I told you, rabbits, something like that. Or also in this case, it seems to be strange, but anyway, we can consider the infected people as predators and as susceptible as prey. Yeah, very quickly ahead. We will see later a little bit the concept of the stability. About the parameter R and A, I already told you R is the infective rate, A is the removal rate of infection, let me say so. Meaning a little bit, why minus here? Because for each contact, of course, we have a reduction of the S, the number of people who could be infected. Therefore, this minus. R is between 0 and 1, when 1 means for each contact we have a reduction, the maximal reduction in the sense, depending on the value of S on I. Again, the contact is stated by the product. This is a little bit a semiotic concept. The symbol recalls the meaning. The product Si recall as the contact between S and I. It's an interesting concept which in mathematics very often we can find. not only in the product, but in other elements which I don't have time now to let me say to tell you. But one example probably known from high school is the integral, no? Which representing a sum, no? We sum up. No? We can see also again in simulate. Okay. Then what we have seen very quickly today, we defined an error. An error in control is the difference between what I want, what I have, and what I want to have. No? I mean, if our goal is to obtain infected people equal 0, it is an ideal goal, but also possible. Again, in control, very important to understand that the goals must be reachable. Must be reachable. This is also interesting in our life. No? If the goal is our goals are not reachable, these goals could destroy our life. No? Also in control. If the goal is not reachable, can destroy not only the control, but also the system. Yeah. Here we have two possible goals. We can basically, yeah, because we have two active, I would like to say, two active population or statement, or excuse me, yeah, states, or in this literature we call, sometimes it's called, the nomenclature is oriented to sessions or compartments. Compartments means states. S is in compartment, I is in compartment, just to give you some boring notation. Why active? Because we can see that this compartment here, R of t, is just the integral of the I. This means we don't have an feedback between R and the rest of the equation. I mean, R does not compare here, R does not compare here. Why that? Because we consider in this model, the scientists Kermack and McKendry considered that once somebody is recovered, cannot be reinfected. Of course, it's an assumption. We have more complex models. I think once I told you, no? The student of this course produced with us in a publication on this. I don't know if I shade ones, it could be in mathematics. Anyway, in which, of course, I show you later again, in order to motivate you to continue to work on this. Or similar systems, no? Using Diesel-Lotka-Volterra. Yeah, once we fix these two goals, I desire it equals 0. And here, excuse me, here, where is, yeah. Susceptible desired equals a value which is not 0 realistically. It's not 0 realistically because we cannot vaccinate all people, or we cannot consider 0 the susceptible people. And this is given by basically by the government or something like that, or in general is a value which can be, we cannot fix alone. Basically, is the value which came from health, let me say, office and so on. And state, this ST, the goal related to the susceptible people, state the immunity. We can see here in a possible definition, mathematical definition, the maximal number of susceptible people. It's clear as an upper bound, not more than. Last time I told you that it seems to be more dangerous to have many susceptible people instead of many infected people. Intuitively, we can understand, no? Because the virus can disseminate quickly. Look, the idea is to find UV, which guarantees S of t equal SD and I equals 0. This is the goal. And we achieve this goal independently of the equilibrium point and so on, considering The second theorem of Lyapunov, I didn't tell you about the mathematical aspect. I just I told you a little bit, but just quickly. I mean, the idea is to have a positive function as a function of the state, or at least, let me say, active state, more important state. You remember I told you R, I told you is a little bit passive state because it's just an integral of I. This means if I am able to control I, R of t is just an integral of this. This means I can calculate R of t. I mean, in Lyapunov function, we can consider just, this is a little bit complicated to express, but what we want to control, what we want to control. I don't know if I told you we have in our lab a Segway, a Segway to travel. The policeman ran with the Segway. We have also a project active there in which we try to control the system using the Lyapunov function. And the Lyapunov function does not consider the movement of the Segway because the goal is that the policeman should run. This means we consider to stabilize this arm of the Segway in the vertical position. This means the policeman try to push ahead the controller in order to reestablish the equilibrium point which we want to have, run away. I don't know if it's clear. If I want to, here it's too difficult to control because too short. You did this exact this is really extremely difficult to control because it's too short. If you put a hand, of course, in order to control, you have to move in this direction here. This in a way to control exactly to realize in a Lyapunov function which don't fix the position of the car. This means the policeman try to push ahead and the controller try to give energy in order to travel in the same direction in order to try to stabilize the arm of the Segway. Of course, the policeman must maintain in order to travel. Just to understand that this method, Lyapunov is known, mathematician from Kharkov, originally from St. Petersburg, but professor in Kharkov. Is really a strong method which can be applied everywhere, in which we have, in all dynamical systems in which we have differential equations and which we want to obtain desired this second theorem, equilibrium points. We will see later very shortly which natural equilibrium point we have. Yeah, here in considering this Lyapunov function, which must be positive in accordance with the theorem, at the equilibrium point must be 0. This is the theorem which I didn't tell you formally. Again, and the function of a positive function of the state, which must be 0 at the equilibrium point. There are many variations of that, but let me tell you really colloquially. Positive function, positive with respect to the state, in this case, or the important state which we want to consider in the control, I and S, and very important, at I equals 0, S equal SD, must be this function 0. You remember last time I graphed the situation. Huh? I think I graphed, but I don't remember. This is the function. If this is SD, here this point is characterized by SD and I0. Huh? If this is SD. Do you remember last time I told you this? We can see that the idea is to find exactly an UV which realize some kind of manifold. A manifold is in the trajectory, is in a surface in which the system is constrained with the dynamics. I mean, again, on this concept, which is quite difficult. This paraboloid here is in a paraboloid if I consider I and S, but I and S are function of t. And this dynamics is quite complex. This means I have to find an UV which allow to say, just intuitively, that independently where I have and over time, I will converge here. This means UV at the end will realize this manifold, this surface, which is, if I consider as a function of I and S, I don't know if you remember in high school or I don't know, in Math 1, did you do Math 1? As a function of I and S is a paraboloid. Or let me say so. Gymnasium. I square is a parabola, right? But I square of t, we cannot recognize in a parabola. At I school, we have y equal x squared. 1 divided 2 x squared. I is our x squared. Excuse me, I is our x. But in gymnasium, we didn't see x of t. This means n x of t is connected with the dynamical system, the differential equations. This means we have to find a UV, which in this context here, and in the meantime, the context of the dynamics, realize, please pay attention, these movements, this means independent of the initial value of I, infected people in the morning, independent of the initial value of S, susceptible people in the morning. If I vaccinate with the UV which I calculated, I will obtain the goal. In the time which I calculated last time, we will calculate very quickly also today. Then we will simulate. Of course, it's easy for the controller, for the vaccination system, if the initial value is close to ST, we can understand somehow. Not only if somehow this axis here is structural in equilibrium point. Now it's difficult to, I can show you in this form. Excuse me if I, inverse pendulum. We have two equilibrium points, this and this here. The same way. Now, if I want to control the system in this point, it's relatively easy, because it's structurally, the system here is structurally asymptotically stable. If I move, I come back here. To control here is more difficult because this equilibrium point is unstable. If I move a little bit, I go away. This means, of course, this analysis of the equilibrium point, which I can do for limit of time just for SI system, is nevertheless important to have an idea how difficult is the control, how can organize this control. This is the most difficult equilibrium point. It's not an equilibrium point. In the sense, it's the most difficult equilibrium point to be controlled. I can control here with the Lyapunov function, with the controller. But of course, here we have the maximum moment, torque. Here, the gravitational force, because of the length of this, is the actor really against this point. Here the system here is to say, to localize, to understand where the natural equilibrium points are, can help us to perform better the strategy of control. But anyway, this can be seen together, or we can see together in the project. Just to justify why today I would like to tell you about the equilibrium points a little bit more in detail. Okay, let me go ahead quickly. The theorem says that I have to find an UV which guarantees these properties. It's a little bit intuitive, you know, the derivative is negative over time. This means I will decrease, colloquially, I will decrease. The calculations are boring. I really tell you again, but really quickly. This is the derivative of V, in which V is this here, which respects the condition of Lyapunov. Then, once I do the derivative, I plug in the model here. Because as I told you, we have an equilibrium, we have a cost function and Lyapunov function, but the Lyapunov function is the Lyapunov of the time. We change over time. Change in accordance with the structure of the model in which we have the input. Now, plug in here I derivative. Plug in here S derivative. Believe me, last time I clarified in detail, doing these boring calculations, I will obtain that I can say if uv is equal to this one, I can say that this part is 0. If uv is equal to this one. Now, if uv is equal to this one, I cannot reach the goal because I can say just in a part of this function here, my function which must satisfy this is just equal to 0. We are far away from our goal. Lyapunov say, I have to find uv that guarantees this. At this moment, just in a small part, let me say, of uv 0. Not negative. But anyway, it's already in a step. Why that? Because if I consider this uv, which includes this part here, and a very important part, which is the switching part, characterized by a sigmoid function. Sigmoid function, probably you heard about the sigmoid function in artificial intelligence courses and so on. I will repeat what a sigmoid function is. Eta is a constant, positive constant. The sigmoid function is a function very important, not only in this course. Why is sigmoid a function? S. It's an ideal sigmoid function. This you can see S. I don't know, with a little bit fantasy, you know. But you can approximate this ideal sigmoid function with hyperbolic tangent. I don't know. Hyperbolic tangent is TGH in MATLAB. I don't remember. I think something like that. Between -1 and 1. If you don't know, it doesn't matter. It doesn't matter. We can consider it hyperbolic tangent of gamma x, in which gamma is the parameter which allows to say that I can approximate the sigmoid function considering gamma 1, gamma 2, in which gamma 2 larger than gamma 1. Positive. Or you can consider arcotangent. Arcotangent probably is no. So this function here can approximate something like that. Larger gamma means better and better approximation of the ideal sigmoid function. This is the mathematical definition. It's a switching function. This means if our x is s of t minus sd, depending. If I have s of t larger than sd plus 1, multiply eta, now we will see. If less, -1. If we reach s equal sd, I have to do anything. Now, in our case, it's something easy because if we are under sd, we are under the value of immunity. This means we don't have to do anything. I mean, this part we don't have. I mean, if the maximal number of acceptable susceptible people is SD, if S is less than SD, you don't have to do anything. Because our goal is not exactly SD. It's less than or equal SD. I show you what I intend. Now, this control law is quite interesting because if you plug in now this expression here, here inside, you obtain an interesting expression. Again, eta is positive. And the expression can be seen from here that this part is negative. Why that? Because this I will cancel. And then I will have here our x, which multiply minus, excuse me, this I will cancel with the contribution of this. Look at this. If you plug in this expression here, in this part of VIS, I will cancel this because of the presence of this. And I will have our x, which multiply minus eta SGN of x. But x SGN of x, I don't know if you remember in high school, is absolute value of x. Do you remember this? I'll show you this property. Why? We can demonstrate. If Sx is positive, this is 1. This is also 1. If x is negative, this is minus 1. This means positive again. Excuse me, I made a mistake in the sense, if x is positive, this is 1, and this is positive, like this. Basically, x equal x absolute value. If this is x is positive. If x negative, this is minus 1, and this negative is positive as absolute value of x. Just to colloquially clarify a little bit this equation, or identity, better to say. This we can understand that this is negative as long as eta is positive. Now, at this moment, we don't, the goal is not reached because we have this expression here once I plug in. But from here to here is clear what I intend because I square can be put in evidence between these two elements, and I will obtain this. Now look, what is interesting this. If, and this condition here will play an interesting role in the next part of the lecture. If S of t is less than A divided R, but now we will discuss again, last time I told you this, we obtain results. With this condition, assuming with this condition, with this Lyapunov function, because Lyapunov function, I can consider a different Lyapunov function. I am free to choose any kind of Lyapunov function. Therefore, the theorem is just in a sufficient condition. Sufficient condition. I mean, if I find the Lyapunov function and I find a U of V which satisfies all conditions which I told you, I can say that the system, or better to say, the point 0, I equals 0, S equals D is asymptotically stable. This means I will reach this. If I don't find, no conclusions, because the condition is in a sufficient condition, but not necessary condition. I don't know if you manage this sufficient necessary condition. The necessary condition says when it's not something necessary, must be, but otherwise we cannot proceed. No? Necessary condition. It's not the case. It's not the case. Sufficient means if I find something, it's okay. If I don't find, I cannot conclude anything. Why that? In this sense, the sufficient is rooted in the free choice of the Lyapunov function. This function which must be positive, must be 0 at the goal, but positive could be any kind, many functions. This means this is interesting. I clarify very well in my course in math for engineers, a master. Could be that some of you will, but in the project we can insist on this. We can insist. Because if it's free, how I can choose something and related to this arbitrary choice. Of course, the result, I mean, the condition which is just insufficient because I can choose another one and then I can find it. But if I don't find, it could be that exists an Lyapunov function which guarantees this condition. When a condition starts with choosing this Lyapunov function, considering a Lyapunov and the function or something, it's just a sufficient condition. Because it could be that somewhere exists something which allows to conclude that exists UV with the rest of the conditions. If, no? In math, we say if. Only if states the necessity. Only if. If we don't have, in German, we say if I have, we cannot do anything necessary. Not pending, in German. Without, not. Okay, excuse me, but could be interesting also this aspect here because, look, this element here, last time we discussed A, which, as I told you, represent again the remove rate of infect. R represent the infection rate. It's quite clear that states an interesting condition. Because basically, if R is very small, what is the meaning of very small? The infection is not so strong because R represents the infection rate. I don't know, from the system is clear. This means if this is 0, we have basically an immunity, we have a contact, because this 0 does not mean as S0 and I0. They have a contact. The product is there. But because of R0, no effect of the contact. Understand how clever is this mathematical expression? Again, we have seen also in Fox's rabbits. This at that time represented a barrier in between. We have many foxes. You remember many rabbits in this room, but they have a barrier. The fox is there, the rabbit is there, and then nevertheless, yeah, the parallelism is not so clear. But here it's more interesting because we have the contact S multiply I, which states the contact, but because of this parameter, which states again the infection rate, how strong is the infection? If this is equal 0, this means we are immune. We cannot be infected. Now with rabbits, yeah, can be done, but means no contacts in the sense because or the rabbits and probably better and the foxes, they are friends, and they don't. The fox does not catch the rabbit, but makes sense nevertheless because we can demonstrate mathematically if you want to work in this area that if you feed with food the foxes, we can mathematically demonstrate that R decreases. The parameters are. I would like to tell you about the identification of R and A. The parameter R decreases because the fox is, let me say, satisfied. This means better than the barrier is this concept as they become friends. Because the fox does not need to eat, theoretically, the rabbits. And this R, at the time was alpha, I don't remember the parameter, decreases. This means even though they have a contact, the foxes don't catch the rabbits because they have food. We can demonstrate this. It could be a nice project also, this. How this is the field in this ethology, when the science, we analyze the behavior of the animals. Ethology, look in Google. Ethology, the behavior of the social behavior of the animals. By the way, we don't have it to learn much. No? If we are satisfied, we are not aggressive. No? Also, okay. And also in the sense here, for large A represents the remove rate of infect. This means, again, that the infection is so aggressive. This means we can allow a lot of S of t. If this is larger this ratio, this means, of course, we guarantee the stability. We guarantee to achieve the results. With this condition, we achieve the results, says the theorem of Lyapunov. But makes sense in the context of our definition of the problem, in particular the definition of A and R, because the ratio A and R state how the infection is strong. Again, for larger and larger value of A divided R, we have the infection is weak and weak, weaker and weaker. It's clear, no? Low, small infection rate and larger remove rate of infect. It means I recover faster. Okay. Now I analyze a little bit what happens because we want to analyze a little bit this condition a little bit more in depth. If I consider this dynamics, which is the dynamics, the original dynamic of S derivative, just 2 slides, no? 1.5. And I put UV equals my UV, which I calculated until now. If I plug in my UV here, I will obtain this equation here. If I do the integral of this is an exercise from Gymnasium, last time we have seen, and I do the calculations, you remember the integral of the derivative is basically the primitive calculated at this point minus the primitive calculated at this point, Gymnasium. Why this integral is minus eta multiplied t? Because between 0 and t is basically 1. If S of t is larger than St. Why this assumption is not so conservative? It allows to reduce some calculations, because we are interested in just in reduce St until, let me see, Sd. We don't have to realize exactly Sd. Or if less than Sd, better. Yeah, this is basically what happens for Sd, and we can calculate T star, which can be seen, calculated, or we can state the time when we achieve Sd for a given initial value of S0, we call it. How? If this could be reached in 1 day, this is given, of course, eta could be that possible very high. No? If T star is 100 here, of course, eta could be very small. This means I need to vaccinate just to understand that if you need to reduce, if you want to reduce the virus in the population very faster, I need to vaccinate a lot of people. Remember, this eta represents the active part of the control, the vaccination, the active part of the vaccination campaign. Concluding, and then we will see something new, considering now this condition here, this is the solution. This is solution combining the dynamic of S derivative with the input. Combining this new information, I will obtain this, which we can see that the initial value of S must be, if you want to have S of t less than A divided R, less than this. This means this is enough to check this. Because if this is guarantees, also this is guarantees because t is the time, which is 0 or larger than 0. Yeah. We will see now a little bit the meaning of this. I mean, if we have seen that if this is not guaranteed, no conclusion. There is another theorem which I didn't tell you, the instability theorem. The instability theorem, which says, basically, roughly speaking, that for condition in which V derivative is larger than 0, the system is unstable. I didn't tell you because we are not interested in instability. We want to control. But we will see that in accordance with this theorem here, that if this is not guaranteed, look here, we have to be careful because this part is positive. If S of t is larger than A divided R, is S of t larger than A divided R, this is positive. This means I have to really vaccinate a lot to guarantee that I will achieve S t. Okay, let me show you a little bit, let me show you very shortly to calculate the equilibrium points, and then we simulate. Let me reconsider the system. Without input, why that? Because I would like to calculate just the natural equilibrium point. Basically, the system itself. Assuming that I don't want to vaccinate, because again, the equilibrium points, as I told you last time, are calculated by U, or the natural equilibrium point, the input 0, and as the equilibrium point, the derivative 0. Why the derivative? Do you remember this? I told you because the derivative represents the changes. Equilibrium in our context means no changes. Makes sense. So no, with the wording. Let me see to accelerate, but I think no, this is too complex. Let me do. Look, this imply let me sketch. Plug it in this condition here. We can see this is 0 if I is equal to 0. But look at this. For I equals 0, I have to say for each end, for each S of t. Did you agree? If I is equal to 0, this is 0, this is 0, this is 0 for each S of t. It's interesting. This means this axis here, all these elements is an equilibrium point. Did you agree with the analysis? Excuse me, equal 0. No, I forgot to say. I told you and then I forgot to. Did you agree this? What is the first equilibrium point? I equals 0, 0 equals 0. But if I is equal to 0, I will have 0 equals 0 independent of S. For each S. Do you understand this language? For each S, independent of S. Also here, this means the equilibrium points is the manifold characterized by the S-axis. This. Therefore, do you remember I told you, if I close this point, not only because I am close to the goal, but the goal is asymptotically stable itself. If I is equal to 0, is the equilibrium point, this set or the manifold, an equilibrium point, an equilibrium set. If I enclose, this means is I is very small. If I is 0, any point is the equilibrium point. But it's trivial because if I don't have infected people, nothing happens. It doesn't matter if S is 1 million or if F is 1 or 1,000 million. It's trivial. Let me analyze again. Look at this equation here. The second equation can be written in this form. Again, the second equation. Yeah, now we can see again the role of this condition, no? S less than A divided R. Because look, if I consider the second equation, we have S of t equals A divided R. You remember, I told you I would like to analyze a little bit. This was my goal. Here for each I, but here I need I equals 0 and I equals 0 here. This means the second condition is I of t equals 0 and S of t equal A divided R. I don't know if it's clear, because from the second equation, which can be written in this form, I can say that S equal A divided R, realize the identity 0 equals 0 for each I, but just for the second equation. But here I need I equals 0, so here I equals 0. This means we have a second condition which nevertheless is quite interesting. If you think, because state in a particular value of S of t. And we will see now what happens in the Jacobian. Let me see the Jacobian. You remember the Jacobian? The Jacobian is the partial derivative of the field here on the right. Look, the derivative of this equation with respect to I is minus R multiply S of t. The derivative of this expression with respect to S is minus R multiplied E of t. With respect to R is 0. The derivative of this expression with respect to R is 0. Let me do the derivative of this equation with respect to I. Minus A. With respect to S, excuse me. With respect to S. The first variable is S. The derivative of this with respect to S. Minus R multiply I. Yeah. The derivative of this with respect to I, now, is R S of t minus A and 0, because here you don't have R. No? The derivative of this expression with respect to R is 0. The derivative of this expression here with respect to S is 0. The derivative of this expression with respect to I is A, and with respect to R is 0 again. Now, I have to calculate this Jacobian at this point and to do the determinant, and then to calculate the same Jacobian at this point. This is a manifold, no? In this set, let me say. And I have to calculate at this point and to do the determinant. Let me do it.
Question.
Yeah, please.
The first row and the derivative with respect to R, because there's an R in there, shouldn't it be like minus S of t I of t?
Here, R is 0. We don't have R. It's not 0. Yeah, it's 0. It's not present.
But there's an R in front of it.
Excuse me, R capitalized is the recovered. This R is the parameter.
That's the infection rate, right?
Yeah, it's fixed. Can be can change, but over time, it's not a state. It's not a state. The states are characterized by the derivative. Change of the number of susceptible, change of the number of infected.
You're right. S of t with respect to R.
But respect to this R, respect to this R,
Ah, right.
respect to the states.
Okay. For the total amount of recovered or removed. Right.
Okay. Let me now calculate this Jacobian at this point, or at this set. This means Jacobian calculated at 0 S of t. This means we have 0 here, 0 here, and this does not change. A is a constant. No? We have 0 here and 0 here, and the rest does not change. This means minus R S of t, 0, 0, 0, R S of t minus A, 0, 0, A, 0. Determinant of this. You remember the determinant. This here, better to say minus 1 up to 2. I plus j, the position of this is 2, up to 2, of what? This element here, multiply the determinant of this minor here, which is 0. No? This multiply this, minus this multiply this. This means 0. Interesting. Did you agree? And if you remember, we cannot conclude. Excuse me. This is the determinant. I have to now to calculate the eigenvalues. You remember the concept of the eigenvalues? You don't remember. I told you. Eigenvalue of this. This means determinant. Excuse me. Determinant of this in accordance. You remember this in math? If you don't remember now, again for the project we will look together a little bit. The determinant of this is not much different as before, because we have lambda plus RST, which multiply again. This we have a minus 1 up to 2. This elementary which multiply this minus this multiply this, which is 0. This means no conclusion, right? Excuse me. I want to go too fast. Yeah. I don't what quest. I have to slow down a little bit. This here, which multiply, this multiply this. I told you correctly, but I forgot this. Yeah. We can see that nevertheless, we have, we can see from here, lambda equals 0, this product. But if you look here, we have an lambda equals as before s of t let me write right. Also for lambda equal this, we have a 0. No? Lambda equal 0 is in 0. Lambda equal this is in a 0. And also lambda, basically we have lambda 1, lambda 2, and lambda 3 equals minus r multiply s of t. Look, this is not a problem because it's negative. You remember, we have to look at the sign of the real part of lambda. This is negative because s is always positive. This says alone no conclusion, but here we need that s of t is less than I divided r. Otherwise, you remember, it's enough one eigenvalue with positive real part to say that the system at this point is unstable. We already demonstrate, we can do also for the other point, which is exactly characterized by this. That's the condition state if the equilibrium point at A R, or in general here, the equilibrium point characterized by the s-axis, because here we analyze the s-axis, is stable, but better say asymptotically stable with this condition. If not guaranteed, we have the instability. Let me show you a little bit the simulations, because it's the time, and then we will come back on this. We tell you again about this sign. Now, the theorem says, as long as all eigenvalues have real part negative, we can say that the equilibrium point of the sets is asymptotically stable. As long as the eigenvalue of at least one, when we have just one positive part, the set of the points is unstable. If we have just lambda equals 0, or at least one lambda equals 0, we cannot conclude. Okay, let me show now the most important part in this 20 minutes. This is the simulation. Let me see if I forgot to say something. I don't think so. Probably I told you something not precise. Let me to be more precise. Yeah. If you consider now the exact point S equal A divided R, you remember this? AI equals 0 as before. And he analyzed here the Jacobian for each S, exactly. Now, if you put here, instead of each S equal A divided R, we have another 0 here. And here we have A divided R. The determinant of this consists of 2 lambda equals 0. 1 lambda 0 here, 1 lambda 0 here. This means at this point here, no conclusions. No conclusions. Then we have to proceed numerically in this sense. Let me show you with the simulations. And then we will show also the control. Okay, let me look here where this is. I forgot to put it. No, I didn't forget. I didn't forget, but it's not connected now. Okay. Ready? SIR. Look. Let me share. I will upload everything. Let me run. Oh, no, it's not this one. Oh, 1 second. Oh, where is now? No, it's not this one. Oh. Okay, I know where it is. I know where it is. Where is this? I think here probably. Okay. Pandemic. Yeah, pandemic. Okay, let me show you. Okay, let me share. Here in this file, we can find many things which we don't use. Basically here, for our system, we have just to consider these 2 lines. We can see very strange number, but the number is realistic because we consider this data we can see here for Germany in March 2020. Data for SIR model. Very important for us, these 2 lines in accordance with the data, the real data. And then look, this is not relevant because we did just this one, eta. You remember this eta? But I think also this is not relevant because I put an eta in the Simulink file. What is important here is this, which is clearly something artificial, just to test with you the immunity level. And then we consider this initial value, but of course, we can see more realistic here. More realistic here from the data which we receive from the newspaper. And then also, it's just in a test. The data which we received is not here, but is in the paper, which if you want, I can show you, because we validated, we worked with the real data. But here for the didactically, the student, one infected, nevertheless, is an interesting test. I can test with 0 infected. You remember, with 0 infected, any value of S of t, of course, is an equilibrium point because no changes, in the sense. Okay, let me run. The analysis which I did now with the equilibrium point must be considered around the equilibrium point. What is the meaning? Do you remember Taylor theorem? You remember the Taylor theorem? Neck-Burwood concept, the derivative. The derivative is connected not exactly at the point, but around the point. Therefore, here, I0 equal 1, no? I0 equal 1. Because if I consider really I0 equals 0, of course, I don't move anything. But the concept of the equilibrium point is if I move close to this equilibrium point, what happens? This example. This example. If I move here around, I come back. If I move here around, I go far away. I mean, I fell down is another equilibrium point, if it exists. If I don't exist, I go to infinite. Okay, let me now look at the simulations. Let me simulate without input. Before simulating, I show you the system. About simulating, I told you a little bit, of course. I told you. Look here. Here inside, we have the system. Here, the input with minus, because inside, here basically is, here we have a minus UV. Minus UV. About UV, I will tell you because came from this. We will see a little bit later. Look here inside. I realized, yeah, but this I told you before, I think. I never told you. The local terra. Anyway, quickly. S of t. What we have here, the derivative of S of t. Because between the derivative of S of t and S of t, we have an integral. You can look here. Integrator is described because it's related to the Laplace form of the integral. I don't know if you remember this from math. 1 divided S in the complex representation represent the integral. It's really the integrator for us. Inside the integrator, I don't know if I share now. No. Between this point here, which represent S of t, and this point here, we have in between the integral. Inside the integral, we have the initial condition, or conditions, in this case, 1 and a condition. You remember, S0 was 10,000, something like that. Oh, no, excuse me, that was SD, the desired. Initial condition was S0, 10,000, 10,000. I don't remember, I have to look. Let me look, S0, S0 was the initial value of which each morning should be given. Let me show you. SD, again, SD was the immunity level. 10,000. S0 is 50,000. This means S0 is larger than SD. This means the system will be what happens. Let me close. Now, S of t, if you look at the equation, is R, you remember, which multiply I multiply S. If you look at the equation, look at this. I multiply S multiply R is this signal here, minus UV with minus R, minus R, but this minus come from here. No? We can also consider without this minus here and include the minus here. It doesn't matter how you realize in sibling. But anyway, the signal here, excuse me, is minus R multiply S multiply I. I is here. We came from the second block, we can see. And S multiply minus 1, everything multiply R, realize my feedback. For the dynamic of I, is quite similar because between I and I derivative, there is an integral. Inside, we have an initial value 1 people which is infected. Here we have R, which multiply S multiply I, minus A multiply I. This is the dynamics simulated inside this block. Now look at the controller. The controller is SD 10,000, or better to say S of t, we can see S of t minus SD, sine of this, remember, minus 1 and plus 1, depending, multiply eta, which here is fixed outside of the M file, for instance, 100, 10 up to 2, minus R multiply S multiply I. Look at this UV, which we calculated together. Why this block here? This block here says that we cannot do anything if S is less than SD. Look. Oh, yeah, it's a little bit different. Okay. This says that's just positive value can be assumed. Makes sense too. Is indirectly says exactly what I told you before. Okay, let me show you what happens without vaccination. Few minutes, I'm ready. Yeah? Okay, let me see. Look at this. Let me see. I am starting from my initial condition, 50,000 something like that. No? And I will end up in one point, which I can calculate also analytically. But we can see also that without vaccination, I will fall down in another equilibrium point in S equal, we can see it where. Why that? Let me show you a little bit this analysis. S0 was 50,000. Now, A divided R. look, let me show what happens. Did you see it? I don't know. Yeah. Look, now, S0, 50,000 is less than this one. Did you agree? 50,000 is less than 75,000, right? Yeah. This means, if you remember, we have the possibility to be stable because if you look, we have something not determined. If you want, I show you. This is guaranteed because if S0 is less than 0, it also guarantees this. You remember this? I show you mathematically. It's very easy from here. No? If this is guarantees, it's guaranteed on this one. But we cannot say anything because it's 0. But it seems to be stable, unstable, no? Because I will fall down in another point. Let me now change. We cannot say anything, and we have to simulate. We have seen that nevertheless we go with another point. We don't remain at this point. Let me see here. Okay. Let me go here inside now. What I want to do? Okay, now let me do another test. Let me consider S0 equal 100,000. Let me run. Again, also in this case, we have an unstable situation because we don't remain at the point. I can share. Okay. We go far away. Let me do another test. And then I show you with the control. Okay, here I didn't check. It's very high. Yeah, the problem I didn't check this. It is really high. I don't know why I put so. Let me do again. Excuse me. I didn't check I, no? The initial value of I. I'm running. Not much differences. No? Basically, we go far away from I equals 0 as before. No? As before. This is the meaning of the instability, no? Because we don't remain the point. I equals 0. This is S. No? We can see here. No? S. No? What is? Ah, no, R. Yeah, excuse me. Oh, I didn't see. 1 second. I'm a little bit tired also. Let me open S. I check always always R. Where is this? Where is S? Yeah. Yeah, but similar situation. I go far away from the initial condition, even though I is quite small. One is one. Okay, let me more interesting probably the control, and then we will conclude. Really, a few minutes. Let me share. With the controller, what happens? The idea, if I connect the controller, which I already clarified, we have to reach independently where I am with respect to initial condition. I have to reach SD, S equal SD, because of this part, a control system, which is our vaccinates campaign. Let me see. Yeah, we can see, as I told you, now we have this behavior starting from the initial value. Do you remember this let me say linear behavior, which I demonstrated mathematically? No? Yeah. Here for R, let me share. Here for R, we have to correct as you proposed. Here R must be at plus UV. No, basically, again, this should be corrected. As your correction is correct, thank you. Basically, this signal here plus UV must be added here, and some, if you want, I do it to calculate the recovery, no? Because the recovery is the integral. This is the integral of the infected multiplied by A plus the vaccinated, as you corrected me last time. Okay, I would like to conclude here. We can discuss a little bit, if you want, about the project and so on. I will upload this material. About that is the last topic. We can eventually discuss the project. If you want, next week by remote, I can tell you about the identification of the parameters in Lotka Volterra. Otherwise, probably this I can do. I am not here, but I can do in remote. Otherwise, we can discuss about the identification of parameters, alpha, beta, gamma in general. Or in this case, we have just two parameters, easier, in another lecture, but up to you. Otherwise, for the students who want to do such kind of Lotka Volterra, it doesn't matter if in the context of SIR, I can tell directly. But if you want in remote, because I'm not here on Friday, but I am in Hamburg, no, this means no problem to connect. It doesn't matter if I am also in another continent. I think this should be the same. Okay, I don't know if you have question about that. Otherwise, for projects or anytime, then I will inform you per email a little bit. Anyway, you know everything about the project and so on. But again, I would like to inform you that the deadline is fixed at the end of September, but we can consider flexible, maximum a couple of weeks. I will inform you in the due time, as soon as I know. If it is flexible, typically, yes. And we have to meet a little bit once, to at least once to fix the project, to fix the topics, and also if you need to discuss during the period of the summer period. Would anyone like to do the project together? Is it a question for me, or? It's not for me, no?
No, actually, I was just asking if someone would like to collaborate for the project because we don't have any group.
Yeah,
So-
if you don't have any group, you can do alone.
Okay,
Or
perfect.
of course. I mean, do you remember I told you the ideal number is 2 students, but you can do alone, you can consider
Okay.
3 students. More than 3 students, I don't have good experience, but it's also possible. I mean,
Okay, perfect.
what is your topic? Do you have a topic?
No, not yet.
Not yet.
No.
What is your background?
I am from environmental science,
Environmental
global
science.
environment. Yeah.
Also, this here in the context of any kind of competition, competition system can be interesting, I think.
Okay, yeah.
I don't know how I can help you.
I actually also had a question that do we have any written document where we are specified on what exactly the details of the project that what we have to do?
Yeah.
Or is it all that you mentioned?
I
Okay.
already sent an email through my study.
Perfect. Thank you so
in which
much.
I fixed, let me say, the conditions in the sense, the guidelines. But the guidelines is very easy. I mean, as I told you, you can do alone. To students is in my opinion, the most suitable group because you can discuss. But anyway, you don't dissipate anyway information with a large group. But three students is also okay. And the topic, you can choose a topic as you want, of course, connected with simulation, optimization, identification, control of the systems. Basically, you can download all material from my study. And typically, once you decide for a topic, but if you don't have a topic, I can give you. The idea is to modify the software which you have, and to adapt that to the problem. I mean, you remember before, just to understand what I intend. Before I told you when an interesting project could be considering this software here, this problem here, to try to analyze what happens if I include also another input, quarantine. This means starting from the simulation, starting from these calculations, we redo the calculation, but the calculations are quite similar, easier because you have two inputs. Starting from this simulation, you have to modify the scheme in accordance with the new, let me say, results from the calculation. Then the project consists of producing a report. How long? Yeah, basically the aim of the report is to document the result which you achieved with the software. This means, in any case, pictures, as I try to tell you during the semester, in a critical form, changing input, changing a little bit some conditions, and to discuss which result you expected, to discuss the results, the obtained results. I don't know, 2 or 3 pages, but it's easy to produce 2 or 3 pages, including pictures. Exactly. I don't know. You see now some picture from possible, from, yeah, for instance, this is exactly the last result, in which you can see that the S of t is decreasing linearly to our goal. Before the results, of course, a little bit about the project. I mean, in the title, 3 lines, an abstract, what we are doing, introduction, the sense of why the problem is important, half page, 1 page, not 2 pages is already too much. If you have some literature, you can cite. And then, as I told you, the kernel of the project is the discussion of the result which you have with the software. You have to upload. I will communicate you where. You find in my study and the folder with the title project for examinations, something like that. It's not yet there. I didn't put, but I will put it. And you have to upload there this report, PDF, but also the software which supported the results. We supported, let me say, the PDF document. This I wrote in I wrote in a communication through my study. Yeah, this is a little bit what you can find also in the communication. But if you want, I can reread again. I can rewrote, and you can reread again. Or everybody can reread again this information. this is a little bit, but of course, to work with at least another student is extremely important. Therefore, I told you is the suitable group, the number of students I would like to say, the suitable number is 2 students, so you can communicate. Because sometimes if you have some problems, it's difficult to solve alone. But you can contact me anytime, and then we can meet here if I am here, or also per Zoom. We can share MATLAB software and results or problem which you have to obtain the results. I don't know. Other questions about the project? Somebody is motivated to work with it was Verma, no?
Yeah, Nagam Verma.
Nagam.
Thank you so much.
You can do also alone, but of course, I understand you, but therefore I told you the more suitable, the group, the ideal group, the ideal number for a group is 2 students. 2 students,
Yeah, okay.
you can communicate. Anyway, but alone is also possible, and I am here for helping everybody, groups and alone, or single people or the students. Because of course, next week, what we can do again about I am not here, nevertheless, about the identification of parameter, or we leave this identification parameter to the specific group. Anyway, not here because I am in Hamburg. Yeah, question. Yeah, at the end, I am here for you.
Yeah.
I am infinite time. I have infinite time. And also, if you want next week per Zoom about the identification, otherwise I will do specifically if the group want to do this direction here, and we need probably to identify the parameters, because the parameter in this case R and A sometimes is given by the health office, let me say, but sometimes must be identified based on the data, historical data. I have a lecture of half hour based on what we did during the semester. If you want, I am for you available next week, the same time, but just in Zoom, because I'm not here. Should I do? No. Okay, but if you want to do a project, we try with SIR, in this case, okay, I am available if we need to identify the parameter. I can tell you a little bit. There are many methods. The idea is to show you one, and my idea was to show you one connected what we did, or what I told you during the semester. But of course, the methods are a lot. Also, PSO is a method in this context, but I don't want to tell you about PSO because you know a little bit already. Because an identification problem, you remember at the beginning of the semester, is an optimization problem. Because God knows the real value. And what we can do as human to calculate parameters which is valid for us. We are not looking for the truth. Just God knows the truth. We have to find a compromise. A compromise is an optimization problem. No? Also in our life, to find a compromise is an optimal solution. Okay, I'm here. I forgot to close the lecture, otherwise. I'm here nevertheless. No? Thank you nevertheless for attending this course. And I would like to leave this open problem identification of parameters for singular groups in the context of the project eventually. Okay. Nagan, thank you also for the participation. Thank you.